So that's where he's my supervisor when I studied PhD at IIT Guwahati. And not only me, there are few more of his students who finished the PhD and are part of this workshop. To name few, Govind is there, Rajib is there, Pati sir is there, uh, Govind, yeah, and also his colleagues like Surya sir is there, who did PhD almost like in a similar time. Um, I mean, the profile is so big, like so it may take half an hour to read out the entire content of his profile, but at least the major highlights of his profile is that like he did MTech at NIT Surathkal and went on to study PhD at IIT Madras under the guidance of Professor Yagna Narayana. So then eventually he moved to IIT Guwahati. So almost like starting his career from 2004, if I'm correct. So till 2017, he was there as part of IIT Guwahati. Then from 2017, he's associated with the IIT Dharwad. So he's currently professor and Dean R&D and Dean Faculty Welfare here. Then apart, like so far he has guided 18 PhD students and still 7 are in the pipeline. I'm one of them. I'm fortunate. So yeah, the sheer hard work and dedication is what we need to learn from him. I mean, and apart, like he also has co-founded 2 companies which are now in at IIT Guwahati campus. So still he has not stopped. The moment I left Guwahati, I thought like I got rid of this person. When he followed to Dharwad, then I was wondering where to move now. But anyway, that was on the lighter note. I mean, I've got so much to credit for him, like whatever I've attained in my life. I mean, past that PhD and his life. I mean, so let's listen to him. I mean, one more character of Prasanna sir to begin with. When I went IIT Guwahati from my company, when I resigned the job and joined PhD at IIT Guwahati. So usually his routine task would be visiting PhD scholars 3 times a day, in spite of having his own classes and other commitments and whatnot. So morning he used to come and take the stock of it, what we were doing, what we have done from yesterday night. So then again, there was one more update that we were supposed to give in afternoon. Then again, he used to come at 6:30 and 7 o'clock. We were at times wondering what kind of update we could have given in 2-3 hours. I mean, so those were the early days by which we started. I think Pati sir and would be knowing much more than me because they were there from the early days. So starting from Krishnamurti sir to I think last student was Pratima, if I'm correctly. Yeah. So totally 18 students, and we were almost 50 people, let alone BTech and MTech students. Just we PhD scholars at the peak of it, like we were 22 PhD scholars when I graduated from IIT Guwahati. So put together around 28 other project staff, a project associate with all the funded projects. We were 50 of strength. All 50 were working on the speech related technologies. Very hard and rare to find such kind of groups, at least in India. So that was the strength of Prasanna sir. Still, I'm sure like he would build the same sort of thing here in Dharwad. Only thing is we should match his frequency. Hopefully we should be able to meet that. With that, like I'll leave it to Prasanna sir to take over the session, sir. Thank you.
Thank you, Deepak. That bottom of the heart words. Able to hear me?
Yes, sir.
Yes, sir. Yes, sir. Yeah.
Thank you, Deepak. So, of course, I should pass on this thing to my teachers, Professor Agnana And also, I still remember when Samudra Vijaya sir came to our lab at speech lab at IIT Madras in, I think, 99 late or early 2000 to teach all of us how to build HMM based system using HTK toolkit. So he visited at a short notice and spent few days with all of us to learn HTK based system for development of speech recognition system. So I'm quite happy that sir is also still continuing to associate and support the speech research activities in India. So with this, so in this session, I will just give a brief introduction to the neural networks and deep learning. Of course, the details of that will be taken up by Deepak in the following session. Of course, many of us know this, but just to give you some pointers who are new to the field of deep learning, I think this all started with, if you people see, there is a classical book by Duda and Hart on pattern classification. There is nothing to do with the neural networks or deep learning, but just to get an introduction to the field of pattern recognition, you should read this book. Uh, then another book is there by Bishop, Pattern Recognition Machine Learning. And the same author, there is one more book which came earlier, which is, I think, Pattern Recognition using Neural Networks or something. That title I'm forgetting. If you just Google it, you will get it. That is also a good book. Of course, there is a very good book written by Professor Biagnana for artificial neural networks. And there is an open book by Michael Nelson on neural networks and deep learning. And there is a good book, Ian Goodfellow, Yoshio Bengio, and Aran on deep learning, which is open book, as well as now they have made a MIT Press official released also. There's a book by Charu Agarwal, Neural Networks and Deep Learning. And just to begin with, you people can watch Ali Godse's Deep Learning University of Waterloo video lecture series and Mitesh Kapra's Deep Learning Part 1 and 2 NPTEL courses. So these are the resources. They're very much well aligned for a novice person to get hold onto the nuances of the deep learning. I have kept my presentation outline in the following way. I'll briefly introduce the field of neural networks and then highlight the shortcomings associated with the neural networks. Because when the artificial neural networks field came, when we were students, Suryakant sir, myself, when we were students at IIT Madras, when we were taking neural networks course, started by Professor Agnana, even though they were projected as we are thinking about deep learning capabilities now, at that time also for neural networks there was a hype like that. Neural networks also will solve problems which are much more efficiently than other models, non-neural models like hidden Markov or stochastic models or something. However, it did not happen like that. So what was the reason for that? I'll explain. Then I will move on to the deep learning, where what is the distinction of neural networks with reference to the deep learning? Because structurally, if you see, both look same. So in that direction, what is that that makes deep learning distinct compared to the neural network literature what we studied earlier? And where is that significant improvement in the performance being coming in the deep learning models? And also the main point is how to train such complex models, which we call it as deep neural networks. What is the training procedure which gave the breakthrough for this deep learning field? Suppose when we take deep learning models, different models you can, I think Umesh sir presented several deep learning architectures. Deepak also will present some temporal sequence modeling deep learning models. When we see all of them on regular basis, we get several deep learning models being introduced by researchers to the different practical applications. Then, so it becomes difficult when we see terminologies like we had deep neural network, then we have convolution neural network, then we have recurrent neural network, Then we have long short-term memory network, gated recurrent units, time delay neural networks, transformers with attenuation, with attention. So many new terminologies are getting introduced into the deep learning. So, but however, if you see them, all their practical usages, we can broadly look in the field of pattern recognition. What we are interested is, we are interested in extracting some features. In the deep learning terminology, we call it as some representations from the given raw data. This is one major task in pattern recognition field. Of course, when conventional pattern recognition was there, this feature extraction was outsourced to the signal processing field, that, as I mentioned in the earlier session. But now that feature extraction is also being viewed as a representation learning in the deep learning framework. So in that way, we can use these different deep learning models for representation learning. Then we can use the next important application in the pattern recognition field is, given a large dimension vector, how do I compress that vector? Because nowadays, as applications of deep learning, um, we are talking about feature vectors of million dimension. So, but the issue with such large dimension vectors is they are very sparse vector. By that I mean most of the dimensions are zeros. Only few dimensions are non-zeros which are capturing the information. So as a result of that, can we bring down the dimension of that large dimension vector to a manageable dimension vector? That is compression. Of course, conventionally, we do it by principal component analysis or linear discriminant analysis. So in that direction, we can also do that by using these deep learning models. That is also another application area. Similarly, when we go for clustering, we can also do clustering with the help of distribution modeling. So there are very, very good distribution modeling techniques that have developed in the deep learning field that also can be looked into. Of course, one of the major applications goes without saying is classification tasks. Classifications we can do by deep learning. And also, as when we work in the field of speech processing or natural language processing, time series modeling is one important application area. So in that way, if you see, the deep learning models have potential applications in most of the pattern recognition related tasks. That means to say, when I'm dealing with some data which is generated by a natural random process or a synthetic random process, like speech, video, image, natural language processing, or any biological sequential data, any general e-commerce data that is generated, all of them will involve one or more of these tasks. We want to extract features, or we want to compress the large dimension vectors, or we want to model the distributions represented or underlying in that data set, or we want to develop classification models, or we do time series modeling. In all these cases, we use deep learning models nowadays. So my suggestion to all of you is, first get hold onto the basic concepts of deep learning and then see that which are these broad areas in which I can use these deep learning models. That will give you the required generalization to get into this field, rather than studying any new model comes, you study that theory and its usefulness separately. Then you will ever be busy with studying new models. What we have to do is, okay, first what is this working principle of this new deep learning model which is coming up? Where is its potential coming? And in which of these broad tasks I can use the deep learning models? So that way, then you can go on expanding your origin in the field of the deep learning. So that is what I wanted to highlight as a part of this talk. If you see neural networks, of course, many of you might have seen pictorial representations of neural networks. Essentially, if you see the genesis for the neural networks, the whole theory and the models that they proposed as part of neural networks they were inspired by the structure and functioning of biological neural networks. Of course, you can watch any of publicly available video lectures, you will get an idea where if you see human brain contains a large number of basic computing elements which we call it as neurons. Okay, there are billions of neurons in our brain, and all of them are connected to one another in a layered manner. That is how any information that is received from the external sensory system gets percolated through these layers of neurons, and finally the required information is derived or comprehended. Based on this observation, inspired by this observation, the researchers in the field of artificial neural networks, they proposed this field of artificial networks, more commonly termed as neural networks. One underlying principle of neural networks as well as deep learning is what is called parallel and distributed processing. Whereas when you go for conventional computing, which is based on Van Neumann architecture, you take the data, whatever you want to process it through the program, apply in a sequential manner, and get the required output from that algorithm. Whereas here in the neural networks or deep learning, we apply the data in parallel, and it is processed in a parallel manner because it goes through several neurons parallelly in a given layer and then goes further, percolates into the. That is why the parallel and distributed processing is very fundamental hallmark characteristics of neural networks, which is based on the observation that is how it may be happening in the human brain, because you have a large number of neurons which are loosely coupled in the form of a hierarchy of layers and then processing. So thus, the original thought process in the neural networks researcher was, instead of using one central processor, what is there in general computing based on Van Neumann architecture, if I have a large number of computing elements which are organized in the form of layers, then I can do this parallel and distributed processing. As a result of that, I may be able to derive more information from the given input data. And accordingly, what was expected was the power in the neural networks is from this parallel and distributed processing network that are there as different models. However, these neural networks need a different way of data processing. That is, if I go for conventional, you have one entry point for data, sequential processing, and then one exit. Whereas you need parallel entry, parallel processing, and parallel exit. That is where you have, it is not one neuron. We have several neurons arranged in a form of layer. So parallelly, you apply the data for all these neurons, and each of them process and forward the data in a parallel manner to the next layer. That is how parallelly the data flow happens, and finally you get the result. So as a result of that, each of those neurons may be looking for different information or a different way of processing. So in that way, we can try to look for different information that may be present in the different data points, parallel data points. So that is how the motivation for the neural networks. The other, why do we need this parallel and distributed processing? One is you will look around for from the same data point, multiple informations you can look around. The second point is again another observation from the functioning of the biological neural networks, that any of our activity on our brain, our biological neural networks, these billions of neurons that are present in our brain, which will provide the redundancy required. Suppose due to any reason some neurons are malfunctioning, okay, but you don't see that difficulty in processing the information because the other neurons, because since there are a large number of neurons, it will help us to still process the information. Whereas if you vis-a-vis, if you go for one central processor, if that processor is down, the whole system is down. So that is one of the motivating factor for coming up with parallel and distributed processing concept. And accordingly, it gives us a graceful degradation. And another point is, as Humesh sir was explaining, the activation functions and that are there in the basic neuron models, we have a nonlinear activation function, rather so which will essentially introduce nonlinearity into the data processing. That nonlinear processing has several advantages compared to the linear processing, so that becomes additional advantage of neural networks. So all these things put forward the field of neural networks as one area of pattern recognition, which will continue to drive, or which are also relevant for the um, deep learning field also. If I go for a central processor, that is only one processor is there, you will have a flowchart or algorithm, then you write a program which will take the input data in a sequential manner, process it in a sequential manner, and produces the output. Whereas when I go for a neural network, it's still also, we need an algorithm, then you need a program to code that algorithm. Only deviation happens from there is the programs are written in such a way, the algorithms and programs are in such a way that it takes data parallelly and process it in parallel manner. What was the very important point, the third important point which I wanted to stress in the case of neural networks and deep learning field is, rather than telling for the feature extraction algorithm or the machine learning model from their mathematical equations or from their working principle that you look for this type of information present in the data, the neural networks and deep learning models say that you explore and learn from data and figure out your own solution. So that is the another hallmark of neural networks. Okay, automatically learning from data rather than in a handcrafted manner telling this is the feature you should look for and this is the way you have to process this data. This we give it to the model to discover the data, and people felt it is a very promising direction. Of course, at that time, when the neural networks field was there 30 years back, the other community did not look at this very enthusiastically, because at that time, signal processing was at its peak. Naturally, whole research field was motivated in the direction that, okay, oh, you're extracting feature, explain us the mathematical equations behind that and clarify what exactly it is doing. If you say, no, the model is learning on its own, they'll say, no, this is like a black box. There is nothing, no information is derived. Of course, still today, even if you go for deep learning also, that comment is valid. People say it's just a black box. We don't know what is happening inside. But the critics are less now, mainly because the performance achieved by the deep learning models is in some tasks comparable to that of human level performance. As a result of that, these critics have come down. However, still that approach is there. How we can try to... So this automatically learning from data sounds promising, which was one of the motivations for neural network field. That in its version 2 and 3 came as what is called machine learning and deep learning. Where machine learning also, as I explained in the previous session, we try to automatically learn the mapping function that is there between the input and output data points. Whereas when I go for deep learning, they're also automatically learning from data. Here it will learn both representations as well as the required functional approximation or the pattern information that is there in the data point. With all these things, the limitation was the performance achieved by the neural networks was not any time to surpass the other models that were there at the field, stochastic models or any other models people were trying. When we want to compare with them, this performance was not surpassing or significantly exceeding the other existing model at that point of time. So that is where people did not take the claims that were given by the neural networks model by the community. And of course, that peak went down at that. Another point I want to say is, when I say these deep networks or deep neural networks, these original conceptual models were proposed by Jeffrey Hinton's group from University of Toronto and few more, Yoshio Bengio and another person. Even 1980s itself. I think again I will take the Professor Umesh sir name, because when we were students, when we were studying neural networks, at that point itself uh, we heard about this time delay neural networks, we heard about this convolutional network, heard about this recurrent neural networks. But uh, even though conceptually they were very good models, at that time there was nothing they were able to demonstrate practically which gives a significant improvement in performance. That is why there were no takers for their proposals until 2006. Okay, until 2006, even though conceptually these models were there, and in some toy studies people were uh, looking about these models, but they were unable to come up with a procedure on how to train these deep neural networks. I'll explain what was the issue in the later slide. Uh, when I say deep neural networks, one of the convention, as all of us, when we enter, we see it has large number of layers compared to the neural networks. Even though that is one reality of the deep neural networks, but the naming of deep neural networks also has another meaning that I will tell. Okay, what happened was, when we were using, say, more than 3-4 layers in a neural network, of course, as any forward neural network architecture, if you consider, the workhorse algorithm in neural networks and deep learning is what is called backpropagation learning. When I use backpropagation learning algorithm, apply the data to the input layer, the data flows through several layers and reaches the output, and the output as a target output decided, and reconstructed output you find out the error between the reconstructed output and the target output, and that error available at the output layer is percolated back. That is why it is called backpropagation of errors. Data is not backpropagated, errors are backpropagated. But what used to happen is, if you have more number of layers, the data, when it is flowing from the output layer towards the input layer, after 2 or 3 layers, the error was either becoming too small. When it is too small, it cannot have any effect on weight adjustment, or it was exploding. So that this is a well-known problem in what is called vanishing or exploding gradient problem in the field of deep learning, neural networks and deep learning. So because of this, we were unable to adjust the weights of the neural network. Suppose you have 10 layers in a deep learning network. Once you take the input data through these 10 layers and reach the output layer, construct the error, maybe from 10th as the output layer, 9th layer, 8th layer, you are able to adjust the weights for those 2 layers. But when you come to 7 layers, 6 layers, and towards earlier layers in the input, towards the input layer, all of them, the weights becomes will not change much. So from their initial random initialization, so as a result of that, it is not capturing any information. So that is how these models were not very useful for any practical task. And that is what people were not knowing how to overcome this vanishing or exploding gradient problem that was there in the neural networks of large size, which they call it as deep neural network. In 2006, Professor Hinton, Jeffrey Hinton from the University of Toronto, his group demonstrated that when you have a deep neural network having large number of layers, we can indeed train such a network, what they call it as greedy layer-wise training. Greedy layer-wise training, that is, you take one layer at a time and train the weights of that network in a greedy manner, that is, with the process of capturing the maximum information flow from input layer to that output layer, when the layer-wise if you take. That is where they demonstrated that, and that then rest was history. Parallelly, this process was taken, and the greedy layer-wise training and people other people demonstrated, yes, it is indeed possible to train PD layer wise. In 2007, other groups demonstrated. Then, okay, the whole explosion started, and now people have other ways of training the deep neural networks. So, as a result of that, that is the starting point, melting point for the origin or resurgence in the field of deep neural networks. With that, what happened was deep learning seemed to have achieved human level performance, at least in few tasks like computer vision and speech processing. And accordingly, there are applications, speech technologies deployed in the practical domain like Amazon Alexa, Apple Siri, and so many other technologies, which will caught attention of the deep other research community, and that is where this deep learning field expanded its origin into all fields of science and engineering. When we say now everybody talks about artificial intelligence making a big wave, the workhorse behind that is this deep learning. So it is not the earlier version of the artificial intelligence of symbolic manipulation. What is that driving this artificial field is the deep learning model. Coming to the deep learning, it is trying to mimic the human way of learning. That is, human way of learning, if you see what we call, all of us learn about any process in terms of experience. Okay, if I want to achieve mastery over certain aspect or certain task, on the first day we may not be very good at that. First, we should get into the basics of that task. First day, we get some feel for that. And then, with continuous practice based on some advice, we will go on improving and over time. For example, many of you may be attending this workshop for the first time. Many of you may be feeling the heat that, oh, this seems to be very difficult, and these so many scripts to be learned, and these models, I don't know this definition of these models, how do they do this script programming. That is the feeling you will have. But when you take some mentoring and continuously practice, you can measure yourself, your proficiency over next 6 months. After 6 months, you will be definitely much better than what you are today. And that is the human way of learning. Okay, you don't learn everything on day one. First, you get onto the minimum required things to become comfortable. Once you become comfortable, then you will go on adding the complexity level to that task. Then with that experience, you will go on learning better. So that is the human way of learning. Learning from experience. Need not specify everything in the beginning. On the first day when you are running these programs, you don't have to know anything too much detailed about that. First level is only just know if you are able to run the scripts properly and generate the output result. That can be a first success what you are going to achieve. After that, you will go in detail of each script and what it is doing, and then see what small manipulations you can do, and then see how the results change. So with that, over time, you will. So in that way, you don't have to hold on to everything in the beginning. Then you can from a novice point, you want to become expert in a task, you can organize that in the form of hierarchy of things to do. For example, to become mastery in using deep learning for speech processing area, if that is your goal after 6 months, how do I break it down into smaller tasks? First level is, okay, somebody else introduces you to this whole framework of how do I install my account in a cloud computing infrastructure, and then how do I take this open source toolkit, how to install them, and how to crunch the data under these scripts written already by somebody else, and just run the programs and make that on your terminal, or your terminal results get generated. Okay, once I'll get first level of confidence, then go to the next level. So like that, hierarchy of way you have to organize. Then what will happen is, once you move to the next level of proficiency, you can link that level of proficiency with reference to the lower level of proficiencies or concepts that you have learned. Okay, thus finally, when you reach that mastery does not come in one day. That is your hard work for several months of work started from a novice as a summer course participant. Same way, this is an example which I took. Same thing you can relate it to any task you do it in life. The motivation for deep learning network is also the same thing. That is, when we say we give raw data for learning by the deep learning networks, many people who are very fancy about feature extraction methods, they will say, what is this without features you are applying to deep neural network? What is that the deep learning model is learning means? We don't have to bother. We don't have to specify what it has to learn. You give the raw data to the deep learning model. The first few layers are expected to learn some representations which they can discover from the raw data. And those representations need not give your classification labels, but they will give the lower level feature representations from the raw data. Okay, the first layer, second layer, third layer, depending on how many number of features you want, how different features you want to extract, different levels of features you want to extract, you can put that stack that many hidden layers. So the representations will learn in the first level, whatever best it can do. Then the data is passed on to the next level. Using those representation learned, the next hidden layer will use that representations and get next level of improved versions of the representations, and goes on like this, starting from a simple representation, a simple feature that is learned in the first hidden layer. As you go deep into the different hidden layers, moving from layer 1, 2, 3, and nth layer, all these features gets combined in such a manner that you start realizing a classification label as you move towards the higher layer. So accordingly, the whole thing, so your ultimate goal, suppose if you take a classification task, your ultimate goal is, given this raw data, identify what is the class information that is there. Suppose if I take classification task, that is the complicated concept. For humans, it is a straightforward thing, but for a computing machine, it is a complicated concept. Given raw data, how do I represent the class? For example, pictorially, if I am given handwritten digits 0 to 9, since I have the training, my cognitive system, just by look at the image of that, I can say this is 0, this is 5, this is 7, like that. That process, if I want to mimic on a computing machine, and that is a very complicated concept. This cognitive task is a very complicated task for the human thing. So that, how do I achieve? That is where, and that can be broken down into learning the simple concept at a lower layers and then combining them to get the complicated concept. So if I go for a deep learning model, when I say you have a large number of layers, and when you flow the raw data from the input layer towards the output layer, as you move from one layer to the other layer, the initial layers will learn the representations, and those representation learning will go on improving as you move towards later layers of the hidden layer, and finally towards the output layers, you achieve the required complicated concept being learned, or the classification label being learned. So that is the motivation for a deep learning model. This I have already mentioned, that is distinction among this one. When I go for pattern recognition era, where machine learning was not there, we used to get handcrafted features from the signal processing, and we used to learning the pattern as a mathematical model. Well thought out mathematical model is there, like a stochastic model. Just to give you an example, Gaussian mixture model, a hidden Markov model. Mathematically, those models will say what is that pattern that they can model, and you can look for that pattern information by satisfying those equations as a form of the algorithm. So in that way, everything is fixed there in terms of when you feed the data. It will not look anything else. It will analyze only from whatever the signal processing algorithm is there. That handcrafting features will happen like that, and whatever the features you give, mathematical models will discover the patterns based on that mathematical equation. They will not do anything more than that. Whereas when I come to machine learning, one degree of freedom was given, where features still handcrafted features, whereas learning pattern is more as a data driven, which is a function approximation, rather than learning it as a mathematical model. Okay, this I want to further say that, caution here, that when we are using now, we'll also call support vector machine, Gaussian mixture model, HMM also as a part of machine learning. So in that way, we are doing pattern recognition through machine learning. But if somebody asks you, how do I distinguish that earlier era of pattern recognition, what we were studying compared to the machine learning, from that point of view, I am bringing out this discussion. Otherwise, we use these terminologies interchangeably. The pattern discovery part is called as functional approximation in case of machine learning, which is a data-driven process. Whereas feature extraction is still using handcrafted features. Whereas when I come to deep learning, both, there is no handcrafted features here. We learn representations as a data-driven process, as well as pattern discovery also as a layered approach, which is also a data-driven process. So entire thing is outsourced to the deep learning model. So if you come to the neural networks and deep learning, if you see, the genesis for machine learning is in the pattern recognition field. Okay, pattern recognition was a well laid out building blocks are there. Each block is meant to do specific tasks, and there is no ambiguity inside each module. Whereas in the machine learning, we emphasize more on self-discovery or data-driven based discovery of the underlying patterns in the input data. That is accordingly, the roots for machine learning is in pattern recognition. Similarly, the roots for deep learning is in neural networks. Structurally, they look similar. Okay, still we use backpropagation algorithm that we are using in the neural networks. And again, it is also goes by parallel and distributed processing and self-discovery of by a data-driven approach. So in that way, for the deep learning also, neural networks as the genesis. Okay, so as I mentioned, deep learning will take care of both learning features as well as modeling information. This point I want to emphasize. Mostly when we say deep learning, why do it's called a deep neural network? Then we say, oh, it has large number of layers. That's why it's called as a deep neural network. Maybe it is true, that is, it is, but it is not just in terms of number of layers, but it is also in terms of number of learning functions, that is concepts that we learn and at different layers, and relating these different concepts when you move to the next higher layer. So that is how it is not just for fun. We go on stacking different number of hidden layers. 10 layer is there, 20 layer, 30 layer, 100 layer we are doing. It is not just like a building block or toy example. There is also a process behind that. We are going to percolate like a distillation process. Starting from the raw data, we go on taking it to different layers so that you derive more and more complicated concept and relate that complicated concept in terms of the lower layer simple concepts that are being learned. So when you are trying to coin this term as concept which is a cognitive task, it's a very difficult thing. So that is where we are able to derive such conceptual information or model such conceptual information using these large numbered layered deep learning network. So that is where that network is also termed as deep neural network. So in that way, both in terms of number of layers as well as the difficult concept that we are trying to model, both will equally contribute for the definition of this model as deep learning model. Of course, if you see relation, artificial intelligence forms the bigger circle. Within that, I have machine learning. Within that machine learning, I have the deep learning. Deep learning is a subset of machine learning. Machine learning is a subset of artificial intelligence. This I have mentioned this point. I will so Jeffrey Hinton group demonstrated that it is indeed possible to train a deep neural network, deep forward neural network, by what is called a greedy layer-wise pre-training of the neural network. Means in the deep feed-forward neural network, if you want to train the weights of each of the hidden layer, so you take out that each layer separately and train it elsewhere as a pre-training process. The pre-trained network, bring them back and put them as stacks and stack them in the deep feed-forward network and just do some final fine-tuning in the backpropagation learning algorithm. That is found to be sufficient for a training strategy in this one. But of course, now we have new strategies for learning this. Other research groups also demonstrated that, and they said that, okay, this is possible, indeed possible. Results are repeatable in 2007. So able to train the deep neural networks, which were not possible before. Okay, so these things I have mentioned already. Here, uh, to the models that we train, these complex models that we are talking about, they have become deeper architectures. However, thanks to the growth of the open source community, we have a lot of open source toolkits that have been developed. It makes our life easy for building deep learning based systems. What fueled the growth of deep learning is this I mentioned earlier: graphical processing units, that is hardware, accelerated hardware structures, and low cost memory, the software infrastructure in terms of open source toolkit, distributed computing, and the codes for different learning models in the public domain, and a large amount of data. So all these factors created an ecosystem for everybody to use deep learning models in their particular research task. One of the things I request all of you to read this paper, Jeffrey Hinton paper, Deep Neural Networks for Acoustic Modeling in Speech Recognition, the shared view of 4 research group. It came in Signal Processing magazine in August 2012, which is a landmark paper which gave a strong footing for deep learning into the field of speech processing. After that, it exploded in the speech processing area. In the last 8 years, everything has become deep learning. Okay, so these points I mentioned earlier. Some important historical points I'll mention. What was at least proven with the help of artificial networks or neural networks for acoustic modeling, it was told that we can it can learn or model the data, or capture the distributions which are distributed in non-Gaussian fashion, better in the neural networks model compared to the Gaussian mixture modeling. That was one of the proposals people looked good, because we are using nonlinear processing units there. And there is one more landmark work by Harvey Bollard and Morgan, which is there as this book, Connectionist Speech Recognition, a Hybrid Approach, which I think openly available. You can download and use it. What they demonstrated was, since that large number of layers we were unable to train the network, they told that even you don't require many layers, you just take one hidden layer of very large dimension. They went in the other view. You don't need to have large number of layers. You have only one hidden layer with large number of nonlinear hidden units. It can be used for predicting the distributions for each of the hidden Markov model states, because HMM was the dominating modeling technique in speech recognition. That is how they mastered. Only thing, at that time, when they 1993, if you see, because this is 80s, late 80s and early 90s work by Harvey Bollard, which came out as a book, neither hardware nor learning strategy were adequate for training the neural networks with many hidden layers on large amounts of data at that point of time. So the performance benefits of using artificial networks with a single hidden layer, what they demonstrated by Bollard and Morgan, or 2-3 layers are not sufficiently large to seriously challenge this duo GMM-HMM combination. Of course, till today we use GMM-HMM combination. At that point, it was not possible, indeed possible, for neural networks framework to challenge or outperform the neural network HMM models. They ended up saying that we can, whatever we model, if you put it into the framework of HMM, we will be able to interpret better or something, or they added some additional features. So the main contribution was in terms of providing some extra features in tandem structure or bottleneck system. That is where the story of version 1 of the neural networks ended. And the training was, as I told, vanishing at exploding gradient problem. And it was a well-known fact that when you have a large amount of data, you will reduce the risk of overfitting the model to the training data, because you have a large amount of data. You will, instead of overfitting, you will become generalization approach, whereas training was computationally expensive. So as a result of that, at that time, people were not very able to demonstrate that. Whereas with these deep neural networks, we we have a better method for modeling the information in the training data and build multiple layers of nonlinear feature detectors. What is this deviation Hinton group demonstrated was, instead of training the entire deep neural network, deep forward neural network together in one go, you take each hidden layer, treat them as a feature detector layers, and then train them separately. That was the thing what they did, and they divided this training procedure for deep neural network into two parts. In the first part, what they call it as pre-training, layer of feature detectors are initialized one layer at a time by fitting a stack of generative models, each of which one layer of latent variables. For example, first hidden layer, latent means hidden variables. For example, if I take speech, MFCC coefficients are the visible variables, whereas the sound unit information which is present inside those represented by those MFCC feature vectors are the hidden variable. That is where in the hidden Markov model, when I'm going to model the hidden state, what I'm talking is about modeling that sound unit information. So when the stack, these hidden layers are treated as generative models. Each hidden layer is treated as one generative model. And when you go for hidden layer is a first generative model. When I take hidden layer 2 is generative model 2, which is taking the output of generative model 1 as input, and using those information, it will try to derive the further hidden information present in that particular set of sound units. So, or set of hidden variables. That is how they. So, what they did was they took each of these hidden layers, treated them as generative models, and stacked them and train as generative models. Once they train as generative models, the weights were adjusted from the point of generative model. Generative model means capturing the underlying distribution. Once they have the generative models, in the second stage, each of these generative model in the stack is used to initiate one layer of hidden units. So the weights initialization in this deep forward neural network is by taking the weights from those generative models, put them as the weights in this layer, and the whole network is discriminatively fine-tuned with the help of the conventional backpropagation algorithm to predict this. And this resulted in a very good improvement in the performance. I think this is repeating the same thing. Just to give one, if you go into that paper, if you see, when they saw on some standard data set, maybe it is timid data set or something, this timid data set, the GMM HMM model which you are trying to develop gave a phoneme error rate of 27.3. Numbers are not important, just I'm quoting. Whereas the final DNN with on filter bank energy that gave 20%, which is an absolute improvement over 7%. Relatively, if you take, it is a sudden jump in 40 to 50, at least 30% in the performance. 7% absolute and about 30% relative improvement in the performance, which resulted in creating a lot of attention for the community to look into deep neural network seriously. So that is the genesis for the whole deep neural network field into the speech processing. Now you will see, suppose if I want to use this feature extraction using deep neural network model, suppose if I take convolutional networks. Mostly when we say convolutional networks, we are trying to use them for classification task or something. But if you really look into each of these convolutional layers are essentially meant for extracting the features from the input. For example, if you take one convolution layer, you apply, for example, the spectrogram as input to here. First, each convolution layer will have three distinct modules. One is the convolution module, another is the pooling module, the other one is the nonlinearity module. All of them essentially process the input data in a nonlinear manner and produces some nonlinearly processed features or representation as output. Those are nothing but the features which are derived from the input data. Whether these features you can directly put into a deep feed-forward network, fully connected feed-forward network for a classification task, or you want to further process those features to further smoothen them, you can add that many number of convolution layers. So in that way, if you see a convolutional neural network, all the convolution layers essentially perform the job of feature extraction or representation learning from the input data. So in that way, one of the major applications of deep learning is you can indeed extract representations or features from the input data. So you can do feature extraction like this. Another thing is the deep belief network, what Professor Hinton group demonstrated for acoustic modeling. This is if you take a deep belief network, what we have is, which is shown here in the right side also. This is not deep feed forward network. It is just a deep belief network which have restricted Boltzmann machines stacked from first restricted Boltzmann machine to nth restricted Boltzmann machine. And when I take each of these restricted Boltzmann machine, this first restricted Boltzmann machine take say MMCC feature vectors as input, and it gets first set of hidden variables H1. And second restricted Boltzmann machine will take this hidden layer 1 output as the input and generates next level of hidden layers. Like that, it can go on to get the outputs. Once you train this deep belief network, if you take the weights that are generated here within each of these random restricted Boltzmann machine, that you can use it as weights in the hidden layers of the deep feedforward network, which acts as the features. The weights are tuned for extracting such features as you move from one layer to the other layer. So in that way, you can use these deep belief networks also for feature extraction. The other thing is, next one is the feature compression. If I want to do, you have a large dimension vector, I want to bring it down the dimension to a smaller dimension, we can use what are called autoencoders, which is also deep autoencoder if you want to use. You have million dimension vector, you want to bring it down to say some 100 dimension or 1000 dimension vector, you can use this deep feed forward network structure where the input is applied in the input layer, the same input is applied as the output layer. That is why it is encoding. Auto-encoding means it is trying to encode the given data on itself by passing this information flow through different hidden layers. And one of the center layer is called as a bottleneck layer, which has a very small number of neuronal elements. And such a compressed layer, what is essentially, you have a wide channel for flowing the data, and you go on constraining the channel width, and it goes through a small bottleneck place where it has to go through that opening only. And that is what is this concept of bottleneck layer here. And you can play with how many number of neurons required in the bottleneck layer. Once the exact reconstruction is possible from the given input data gets exactly reconstructed at this point. So to that extent, you adjust neurons in the bottleneck layer, and then you take the output from this layer. You can remove this decoder part and take the output from here. Then you can use them as compressed feature vectors for any classification task. So in that way, which we are doing by PCA or LDA, we can easily do by this deep neural network. So this is another application of deep neural networks. Similarly, suppose I want to model the distributions of the deep neural networks. We have what is called the variational autoencoder, which is a variant of the basic autoencoder that we studied in the previous slide, which was meant for data compression, which essentially compresses the large dimension vector to the smaller dimension vector. Whereas here in the variational autoencoder, we don't just capture, get the compressed vector. What we try to get in the work on this bottleneck layer is capturing the distribution represented by these large dimension vectors. Okay, the distribution where, for example, if I want to capture the mean and variance associated with those compressed feature vectors. The advantage of that is I am not reconstructing the compressed vector for the input data. I am able to sample the data from this distribution. Any number of new samples can be generated. Once I train this variational autoencoder, I can only use the decoder part. With the help of this distribution that is captured, I can go on sampling that through the decoder network to generate new data samples. That is what is distribution modeling. In this way, this bottleneck layer will model the underlying distribution represented by these data points. Once your distribution modeling is nothing but your generative modeling, you can use variational autoencoder for the distribution modeling. And one of the other successful model is generative adversarial network, GAN network we say. Simple concept is that network will have deep neural network will have two parts. One is called the generative network. The other one is the discriminative network. The generative network will generate the data, taking random noise as input and go on adjusting the parameters of the generator network such that it will generate the target distribution information. For example, random noise, there is a specific distribution, whereas if I take the speech signal, it has its own set of specific distribution. Now, starting from that random noise distribution, I want to reach the speech signal distribution, and that is what is the reference point for this generator network to adjust its weights of its network, deep neural network, such that it approaches towards that generating the distribution samples corresponding to the actual speech data. For that purpose, you have some real speech data, which I don't apply to the generative network. I have a discriminative network, another neural network, which will try to compare the data generated by the generative network with the real data, and it will find out the error. Based on that, it will decide a binary decision, whether it is both are same or different, false or true. And that information is fed back into the discriminator network as well as the backpropagation, this generative network, to adjust their weights. Each of them, generator network and discriminator network, will try to compete with each other. Generative network will try to fool the discriminator network. Discriminator network will try to catch the fooling by the generator network. The time at which the discriminator network will fail to find the discrimination between the generated data and the real data, at that point of time, the generative network has been well optimized. The weights of the network have been well optimized to generate more and more data. Nothing but these weights have captured the underlying distribution of the data that is being generated. So in that way, we can use the generative adversarial network for distribution modeling, which is also a well-known deep learning model. Of course, this is deep feed-forward network is a very classical model which is being used for classification tasks. You have input layer and several hidden layers are there, and each of these hidden layers are obtained. The weights of these hidden layers are computed from other generative model training and stack them like this, and then use it for a classification task. You can use it for, so even if you take this convolution layer, the fully connected layer, what I am talking about, it is nothing but the deep feed-forward neural network layers are used there for classification purpose. So in that way, when I say CNN, I am using for classification task. First few layers we are using for feature extraction or representation learning. The last few layers will be deep feed-forward neural network for doing the classification task. So far, all the learning models that we have explained, for example, when I go for variational autoencoder, generative adversarial, deep feed-forward network, restricted bold formation, any of these deep learning models, they assume there is no timing information present in the data points. Even if it is there, it is not giving weightage to the timing information while modeling the information. Whereas when I take speech, essentially the information is stored in the time series. That is, timing information is crucial to discriminate among different patterns or informations or concepts that are present in the speech data. And there are several deep learning models that have been proposed for this time series modeling using deep learning, like time delay neural networks, recurrent neural networks, long short-term memory networks, which I think Deepak will describe in his talk, followed by this. I will not go into detail. His whole session is on that. To summarize, so I know I emphasized on what is this neural network about and what was the genesis for the neural networks, and when the breakthrough came in the deep learning area, what is the training process for the deep neural networks, then what are the different tasks in which we use deep neural networks. We can use it for feature extraction or representation learning. We can use it for data compression, or we can use it for distribution modeling, or we can use it for classification tasks, or we can use this for time series modeling. Maybe I might have left some other tasks, but these are all the important tasks in the pattern recognition field, which deep learnings can be effectively used for building the models. I think with that, I'll stop it here. Sorry, I have taken about 7 minutes more. I'll be happy to take any questions any of you have. So, Amrut has a question that does neural network gives better results if you use raw data compared to that of the processed data? So it will not give, because if I take raw data, you need several layers first to derive the representations, and then in the later layers combine those representations to do the classification task. So if you just if you take a neural network, what we are talking about 1 to 3 layers networks, by the time you reach the third layer, you're just only some representations are not learned. They are not matured enough for doing any classification task or any concept that you are looking for. So accordingly, it will not give better performance compared to deep neural networks. So that is why when we were using neural networks, when we used the raw data, even we had written a paper on applying linear prediction residual directly to the autosticity neural network model and try to model the speaker information. So at that point of time, people did not appreciate that effort, saying that no, it will not capture any information. But of course, finally they agreed, and we have a paper published in 2006, Speech Communication. Of course, the modeling is not that great there. We only conceptually showed that, but to summarize, neural network will not give better results if you use raw data compared to the deep learning.
Hello, sir.
Yes, Sajal.
Suppose I am working on a language that I have 10 hours or 50 hours of data, then deep neural network will not be effective for me now.
What is your question?
Suppose I am working on a language that's I have a very less amount of data, say 10 hours of data or 50 hours of data. Say in deep neural network, there is no use for me. Is it?
So the answer is yes as well as no. Yes, because if you have only that data and you can build system only using that data, then it is yes, that you may not get better performance. No, in the sense that now the recent studies in the deep learning models are such that you can, just like we do the pre-training of the networks in the generative concept, what they did for demonstrating for acoustic models, you can do the pre-training of your deep neural network using the speech data from other languages to capture those representations. Okay, essentially to capture the feature detectors, and then use those pre-trained network on your 10 or 50 hours of data. At that point, it's still you may expect to get the better results.
Okay, thank you, sir.
Yeah, you should not discount outright. Okay. Any other questions? So otherwise, thank you very much. Thank you, Deepak.
Thank you, sir. Thank you. Yeah. So shall we give a break, or what do we do, sir?
No, it will be you, whatever you.
Okay, we can have 5 to 10 minutes break. Like maybe we'll start at 11:20. Is that fine?
Yeah, I think Deepak sir, you can give 10 minutes break, then we can start.
So
11:20 is fine.
Yeah, so we'll start at 11:20, sir. Yeah. Okay then. Yeah, we'll meet at 11:20.